Okay, now we have the monotone convergence theorem, which states a monotone sequence, which means it's increasing for all values in front of it, or it's decreasing for all values in front of it, is bounded if and only if it is convergent. And further, if it's monotone increasing, this implies that the limit as n approaches infinity of xn is equal to the supremum of xn for all n's in the naturals. Or if it's monotone decreasing, the limit as n approaches infinity of xn is equal to the infimum of xn as n for n in the naturals. Now the supremum is the least upper bound and the infimum is the greatest lower bound. So let's just think intuitively, if the supremum is an upper bound, we can subtract some arbitrary value from the supremum that will be less than some element of the sequence, and then that will be less than the supremum itself. So let's just think about that for later. So for our proof, we want to show that given monotone increasing and bounded, both of our conditions, we want to show that, I've already written that, but it's okay. Want to show that xn converges to the supremum for xn and part of the naturals, or want to show that given monotone decreasing and bounded, xn will converge to the infimum of xn for n in the naturals. Okay, so let's start with the increasing case. So assuming xn is monotone increasing and bounded above, which means it's increasing for all values in front of it and it has an upper bound, this implies that the supremum exists. So hence, the supremum exists. So let's just call the supremum A. Now, we can say by definition, for all epsilon greater than 0, there exists n in the naturals such that A minus epsilon is less than x big N, which is less than or equal to A. Now, what this is essentially meaning is we can choose a value in the sequence x big N, which has to be less than or equal to the least upper bound, the supremum. But then we can choose an arbitrary epsilon so that the least upper bound minus that epsilon is less than that value xn that we picked. So from this, we can say that there exists an n greater than or equal to big N such that A minus epsilon is less than x big N, which will be less than x little n, which is less than A, which is less than A plus epsilon, just intuitively, because A plus epsilon will have to be bigger than the supremum itself. So now we can do a similar method of just considering the strict inequalities for the item we want, which is xn. So A minus epsilon is less than xn, which is less than A plus epsilon. And now, since we have two items on either side of the inequality, we can put xn in an absolute value and say xn minus A in absolute values is less than epsilon. And this is exactly the definition of a convergent sequence, given A is the limit, which we've defined above here. So now let's look at the decreasing case. So we can assume xn is monotone decreasing and bounded below. So given this, the infimum must exist. So let's call another value B the infemin. Okay, so similarly, by definition, for all epsilon greater than 0, there exists big N in the naturals such that this greatest lower bound, B, will be less than or equal to some value xn, which will be less than B plus an arbitrary epsilon, similarly to what we did above. And then, thus, there exists little n which is greater than or equal to that n, such that B minus epsilon, which will have to be less than the least upper bound, is less than B, which is less than xn, which is less than or equal to, so this should be less than or equal to x little n, which is less than B plus epsilon. Now we can just isolate this xn between the two strict inequalities. B minus epsilon is less than xn, which is less than B plus epsilon. And now putting this with an absolute value, xn minus B is less than epsilon, which is also the definition of convergent sequence, where we have xn minus L is less than epsilon. So that's our proof for both the increasing and the decreasing case of the monotone convergence theorem.